In this segment, we're going to talk about how to take uniform random draws and turn them into draws for some arbitrary random variable. Now, strictly speaking, this is not something that you're going to use that often in practice, because we have lots of handy functions for simulating from different probability distributions in R, as we saw in our second segment. But I promised to show you a little bit more about how things work under the hood. And this is the crucial ingredient that takes you from, say, the Lamer random number generator that we looked at in the first segment, to draws from some other distribution that you may be interested in. It's also a nice way to think more deeply about CDFs, quantile functions, and what it means for a random variable to have a particular distribution. So here's how it works. Suppose we have a way of making uniform draws, but suppose that we actually want draws that simulate a random variable with CDF capital F and corresponding quantile function q. Well, if we have a simple way to evaluate that function q on our computer, then we can use the following technique to obtain a draw of a random variable with CDF f. Here's how we do it. First, make a single uniform draw, uniform on the interval 0 to 1. Then plug this draw into the quantile function q and set y equal to q of u. If you do this, then the probability that that resulting random variable capital Y is less than or equal to the threshold little y will be exactly equal to f of little y. In other words, we have found a way to make a random draw with the desired CDF capital F. If capital F is a continuous and strictly increasing function, then this quantile function is merely f inverse. Otherwise, q is the generalized inverse of f. So the continuous strictly increasing case would correspond to our familiar continuous random variables. But if we want to look at a discrete random variable, we'd need to worry about the generalized inverse. If you want to read some more about that, you can click on the link and see a very helpful explanation from Wikipedia. But let me take a simpler case. I'm going to take a CDF that is indeed continuous and strictly increasing. This is the CDF of an exponential 1 random variable. It's actually the random variable that you examined in the exercises at the end of segment 2 of this lecture. And the CDF for this random variable is 1 minus e to the negative x. So remember that a CDF spits out a probability. So I'm going to call the output of that function 1 minus e to the minus x, little p. So little p is equal to 1 minus e to the negative x. Now, to find the inverse, I simply need to rearrange this to solve for x in terms of p. When I do that with a couple of lines of algebra, what I get is x equals negative the logarithm of 1 minus p. So that means that the quantile function in this case, f inverse of p, is negative log of 1 minus p. Remember that the CDF takes in a value along the horizontal axis, so a real number x, and spits out a probability p. That means that the quantile function does the reverse. It takes in a probability p and spits out a value along the real line, little x. So what I'm going to do now in this code block at the bottom of the slide is implement the inverse transformation method using the quantile function that we've just derived. So in the first line, I'm going to make a large number of uniform random draws, and then I am simply going to transform them according to the function minus log of 1 minus p. So I'm plugging in u for p. So uniform random numbers are on the interval 0 to 1, so they're perfectly valid inputs for this function that's supposed to be taking probabilities as its inputs. And then I'm going to make a histogram of the result. What do you know? It looks exactly like it should. It looks just like in an exponential 1 distribution. Now, you might quibble that it's difficult to eyeball the shape of a distribution from a histogram like this, and I would agree with you. So I would now like to introduce you to a slightly more general and more precise way of checking whether you really have draws that match some target distribution. But before I do that, I would like to show you a little proof of why the inverse transformation method works. So first the proof, and then a better way of seeing that the draws that we've created really do come from the distribution that I claim they do. Now in the proof, I'm going to make the simplifying assumption that f has an inverse. So I'm going to be assuming that the CDF is continuous and strictly increasing, so it has inverse F inverse. The claim here is that if U is a uniform 0, 1 random variable, then Y, defined as F inverse of U, has CDF F. Okay, so we'll start off by saying, well, what is the CDF of Y? That's just defined as the probability that the random variable Y is less than or equal to some threshold, little y. Now, by definition, capital Y is equal to F inverse of U. So in my first equality here in the middle of the slide, I'm simply substituting F inverse of U for Y. In the next step, I'm going to be relying upon the fact that since F is strictly increasing, x1 is less than or equal to x2 if and only if f of x1 is less than or equal to f of x2. So what I'm going to do here is I'm going to transform both sides of the inequality inside the probability statement using the function capital F. I'm just applying capital F to both sides of the inequality. The reason that this is equal to the line above it is because it doesn't matter if we describe an event in a different way. As long as the meaning of that event stays the same, the probability stays the same. So the statement F inverse of U is less than or equal to little y is exactly the same statement, logically, as F of F inverse of U is less than or equal to F of little y. And the reason for this is, as I just said a moment ago, that capital F is strictly increasing. So it preserves the ordering. It preserves the direction of the inequality. But F is the inverse of F inverse. That means that F of F inverse of anything, call it x, is just that thing, x. So in the third line of the mathematics that I've displayed in the middle of the slide, I'm simply going to use the fact that F of F inverse of U equals U. And I'm leaving everything else alone. Finally, we have to ask ourselves, what was U? Well, U was a uniform random variable. And so what is the probability that a uniform random variable U is less than or equal to f of little y? F of little y is just a number. Little y is some real value, and f of little y is some probability. So we can just think of f of little y as some number between 0 and 1. And we're asking the probability that capital U is less than or equal to that particular number. Well, the CDF of a uniform random variable is very simple. The probability that U is less than or equal to little x is just x. And here, in the mathematics I've displayed in the middle of the slide, the role of x is played by f of y. So we have shown that the probability that a capital Y is less than or equal to little y is exactly equal to f of y, proving that the inverse transformation method works as advertised. And now, as promised, I want to show you a better way to check that the draws you think come from a particular theoretical distribution really do. This technique is called a quantile plot or a QQ plot. If you've never heard of QQ plots before, you may want to take a look at this blog post that I wrote. The blog post is actually about the central limit theorem, but towards the bottom of the post, I go into much more detail about QQ plots. But for now, we only need to have a basic understanding of how they work. So the idea of a QQ plot is to compare theoretical versus sample quantiles. We want to ask the question, do these draws, these supposedly random draws, really come from that distribution? We can also use it to ask if two sets of draws come from the same distribution, but in this instance, we're going to ask whether some sample quantiles match some theoretical quantiles. So here's how it works. We're going to define the x-coordinate in our plot to be the quantile function from some theoretical distribution. So that might be, say, the normal quantile function, evaluated at some probability p. Then we're going to set the y-coordinate of our plot to be the sample quantile of the same probability p. So by choosing a p-value and plugging it into each of those two quantile values, we're going to get x and y coordinates that we can display in a plot. If we vary p between 0 and 1, we consider all the different probabilities that we could plug in there, we're going to get a whole range of points, a whole range of x and y coordinates, and that will give us a plot. I'll show you one on the next slide. But before I do, I want to tell you briefly how to interpret these plots. If the y and x points line up, in other words, if all the y coordinates equal all the x coordinates, this means the sample and theoretical quantiles agree perfectly. If they don't line up on the line y equals x, but they line up on some other line, say y equals mx plus b for some m and some b, this means that the theoretical and sample quantiles agree after centering and scaling. So this would mean, well, the two distributions are not the same, but if you were to transform them to have the same mean and the same variance, they would be the same. And here is an illustration in which the two are definitely not the same. These points do not line up on the 45-degree line, and they don't in fact line up on any line. They curve away from what appears to be a relatively linear relationship towards the middle of the plot. So again, the x-axis gives the theoretical quantiles, the y-axis gives the sample quantiles, and each of those points corresponds to a probability little p at which we are evaluating the two quantile functions. So what I've done here is I've shown you that the t distribution has heavy tails relative to a normal. I've chosen a t distribution with 3 degrees of freedom, which ensures that it actually has a mean and variance that are well defined. And I have made 500 draws from this distribution. I'm stacking them up into a tibble, and then I'm using ggplot to make my QQ plot. The way that I'm going to do this is with the geom called geom_QQ, and that geom requires an aesthetic mapping that specifies the source of the sample quantiles. So here I'm saying sample equals x to say, hey geom_QQ, you've got to go find the sample quantiles. I called them x, so look for them under the name x. Now you might ask, where are the theoretical quantiles? Well, if you don't tell it otherwise, geom_QQ is going to default to providing the theoretical quantiles of a normal 0,1 random variable. In other words, a standard normal random variable. Now here's a plot that looks a lot better. What I've done here is I've made a slight change. I've still got exactly the same sample quantiles because I'm using the same random draws as before, these T3 sims. But now I'm specifying a different distribution in the third line of my code block. So here in geom_QQ, I say distribution equals QT, which means I'm telling R, hey R, I want you to use the quantile function QT, Q stands for quantile, T stands for T distribution, to evaluate the theoretical quantiles. And I'm also providing it with a list of parameters. I specify these with D params. D stands for distribution, so the distribution is QT, and the D params are a list with one element, df equals 3. So I am supplying the argument degrees of freedom, df, to the function qt, and I'm setting that equal to 3. And indeed, in that case, I'm using exactly the quantile function that corresponds to the distribution from which I made these draws. So up to a little bit of sampling variability, these points do lie on the 45-degree line, as they should. To make it a little bit easier to see this, I can add one more line of code here. So you'll see that everything in lines 1, 2, and 3 of this code block is the same as in the previous slide, but I've added something new on line 4. Namely, I've added geom_QQ line. This creates a quantile line that tries to go through these points. The way that you specify it is pretty similar to the way that you specify geom_QQ. So I've got to say what the distribution is that I'm going to use for my theoretical quantiles, QT, and I've got to set the distribution parameters, df equals 3. I've also chosen a red line to make it easier to see, and indeed, this looks like a pretty good fit, which isn't that surprising because these really are T draws. So the line is actually going to go through the first and third quartiles, so the 25th and 75th percentile. So what's happening here is we're taking the 25th percentile of the sample along with the corresponding theoretical quantile, and we're doing the same thing for the 75th percentile. 2 points to find a line, and that's how we get our red line. So now we're actually ready to do a better job of looking at our supposedly exponential 1 simulations from before, the ones that we made using the inverse transformation method. And indeed, they look pretty good. So all that I've done here is I've changed which random draws I'm using to compute my sample quantiles. So now I'm using exp1 sims, which we generated a few slides back. And I'm also changing the theoretical distribution against which I'm evaluating. So rather than qt, I'm using qexp, and I've got to pass the parameters rate equals 1, and that's it. Again, I've drawn the QQ line just to show you that these do line up pretty well on the 45-degree line. So now it's your turn. I've only got one exercise for you this time, but I've given you a random variable with a sort of unusual density. This random variable may be one you've seen before, it may not be. You might like to draw a picture of that density to get an idea of what's going on. And what I would like you to do is to use the inverse transformation method to simulate IID draws from this distribution.